All right. So you have a 30-meter truck moving at a speed so that gamma is 15. And then there's the garage. The garage is 6 meters long. Question is, can the truck fit in the garage? Okay. And we're going to consider two events from two different reference frames. One from the frame of a person in the garage, let's say us. We're going to watch the truck come into the garage. What are we going to observe? So we're going to consider two events. Event number one, the back end of the truck clears the front door of the garage, and the front door is closed. So basically, we're going to consider, so here's the garage, and here's the truck. That's event one. Event two is when the front of the truck hits the back end of the garage. When event one occurs, we're going to set our clocks to 0. So that the clock on the truck is 0, and the clock on our clock is 0 also. And we're also going to consider this to be our origin for both coordinate systems. When the back end of the truck hits the front end of the garage, we're going to call that x equals 0. So we have two events to analyze. What do the two observers observe? Okay. First question, if a 30-meter truck is going so fast that gamma is 15, and we see this thing coming towards us, how big is that truck? Let me fix one more thing, sorry. Okay. How big is that truck? Well, wouldn't the truck be Lorentz contracted by a factor of 15? And I'm going to have to erase these equations, I apologize. But the truck would be contracted by a factor of 15. So to us, in the garage, truck is 30 over 15, 2 meters long. So to us, the truck is going to be 2 meters long. So to us, we're going to observe the truck do this, and the truck do this, and the front end of the truck, since this is 2 meters, is going to travel a full 4 meters at the speed such that gamma is 15. How long does it take the truck, the front end of the truck, to go from this point to this point? Well, I know the truck is going to travel 4 meters, and so the time, according to us in the garage, we're going to call ourselves the unprimed frame, is going to be 4 meters over the speed that gives us gamma is 15, which ends up being 0.9978 C. And this takes 13.4 nanoseconds. Okay? So what are we going to observe? We're going to observe the back end of the truck clear the front of the garage door, and then we're going to observe the front end of the truck clear the back end of the garage. Okay? Now, what is the person on the truck going to observe? Okay? What's the person on the truck going to observe? All right, sorry. There's a picture of what's observed in the garage. Well, what about the person in the truck? Well, I can use the Lorentz time transformation to calculate what time the truck will measure when we see that the truck is at this location. Okay? What's the Lorentz time transformation? And this will be I think this is mind-boggling. Since the truck is moving relative to us, the truck is in a prime frame. Okay, so T prime is the time when the truck, as observed by us, hits the back end of the garage. So I'm going to call this T prime truck 2. And this is the time measured via the garage. This is the 13.4 nanoseconds. And really, and the front end of the truck travels 4 meters. Really, these should be deltas. But that's okay. And no, these are not deltas, sorry. Never mind, forget that. Okay. This is the position of the front end of the truck. So this is 6. This is the speed of the truck. And then gamma is 15, so let's put in gamma is 15. So let me rewrite this. Of course, C is 3 times 10 to the 8 meters per second. So we observe in the garage, we in the garage observe that the truck is trapped in the garage for 13.4 nanoseconds. What does the truck observe? So what does this turn out to be? It turns out to be a negative number. It turns out that this number is minus 98.9 nanoseconds. What does a negative mean? It means that the truck sees the events reversed. It means that the truck sees this event first and then the other event second. Yeah. And that's okay because the two events are not related by some sort of cause. In other words, if there was a force producing, if there was some sort of force involved that produced motion, the events could not be time reversed in the two frames. But these two events they're not really causally related, and as a result, they can be reversed in time. So this is what the truck sees. Those are the two events that the truck sees. Now, we can calculate the amount of time the truck spends in passing the garage, such that the back end, the time difference between when the back end of the truck hits the front end of the garage and then the front end of the truck hits the back end of the garage. That distance traveled by the truck is going to be (30) minus the length of garage as measured by truck divided by the speed. Of course, according to the truck, the garage is contracted by a factor of 15. It's only 0.4 meters long. And so this time ends up being 98.9 nanoseconds. Let's make the problem a little bit more interesting. Let's talk about the same problem, but this time, instead of letting gamma be 15, let's let gamma equal 5. So let's assume this time the truck is traveling so that gamma is 5. Now that, according to us, the truck is 6 meters long. What does that mean? It means when the back end of the truck coincides with the front end of the garage, simultaneously, the front end of the truck is going to be at the back end of the garage. The entire thing is going to be inside simultaneously. So the two events are simultaneous now. Okay? So if we let gamma equals 5, events 1 and 2 occur at the same time. And if we set t equals 0 for event 1, according to us in the garage, t is going to be equal to 0 for event 2. What about for the truck? Again, we go back to this equation. Okay, now this is on the truck. This is what the truck is going to measure for the time when the front end of the truck hits the back end of the garage. This is going to be 15. In our frame, since gamma is 5, sorry. In our frame, since gamma is 5, the two events are simultaneous, and since we set the clock to t equals 0, this is 0. And the speed then is going to be a little bit different. I had to write it out to a lot of decimal places. So I get 5 so I get 5 for gamma. When you do this calculation, this number turns out to be minus 97.98 nanoseconds, which means again that the truck is not going to see the two events as simultaneous. Okay, the truck is going to see the second event occur first. So and I have a mistake there. To the garage observer, the truck is 6 meters long. That should be 6 meters, sorry. And to the observer in the garage, the truck, to the driver, I'm sorry. To the driver, the garage is 1.2 meters long. What happens if the truck stops in the garage? If the truck stops in the garage, now the truck is not in an inertial frame. We have to describe everything in terms of the person in the garage frame, us. If we observe the two events occur simultaneously, when the truck comes to a stop, once the truck comes to a stop, they will observe the same two events occur simultaneously. What if the back door of the garage was replaced by a very thick concrete wall and the truck slams into the garage, that garage wall? What will happen is when the truck slams into the garage wall, there's going to be a wave sent from the front end of the truck to the back end of the truck. That wave takes time to get to the back end. So in the time it takes, while the wave is traveling to the back of the truck, the front end is collapsing and compressing, but the back end is still going at a constant speed because it has yet to experience that force because the wave hasn't come down. And so the front end of the truck compresses, the back end keeps going at the same speed. The front end of the truck changes speed, the back end does not. And it keeps going at the same speed until it receives the information from that wave. And as the truck comes to a stop, eventually they're going to be observing what the person in the garage is observing. You can't say that once the front of the truck hits the wall, the back end is going to stop. You can't say that because that assumes that the wave travels from the front end to the back end instantaneously. Okay. That also means that objects aren't rigid. Okay. There's no such thing as a rigid object because the wave has to travel from one end of the medium to the other in a certain time period because it can only be transmitted at the speed of light. One can spend a lot of time discussing these problems, this particular problem, and folks do. If you go online, there's a Wikipedia page on the pole in the barn paradox. This is really the pole in the barn paradox. Okay, the only difference is somebody's running with a pole into a barn. In our case, the truck is the pole and the garage is the barn. But if you're really interested in knowing more, I can only give you a small taste of this problem. You can go online and either on, just look it up on Wikipedia. I have a book called Understanding Relativity, and the author is Sartori. And in this book, he goes through the twin paradox and the pole in the barn paradox in great detail in analyzing it from just various ways. It's very well done. So if you're interested, and by the way, there's no calculus in it. It's all algebra. You only need to know high school algebra. Okay, so it's done in a very nice way. It's very conceptual. So if you're interested in learning more about it, go ahead and read that. Okay. So now I'm going to talk about another topic that must be concerned with in relativity. And again, as I go through relativity, I'm just summarizing some of the high points in relativity. One of the things we have to think about in relativity is, how are the concepts of mechanics affected by these postulates? It turns out, and I've probably mentioned this the other day, if you apply the Lorentz transformations to all the important equations, or all important laws in electricity and magnetism, that they're going to look the same. If you apply the Lorentz transformation to Maxwell's equations, no matter what reference frame you're in, the equations are going to look exactly the same. Okay. In mechanics, there's a problem. If you apply the Lorentz transformation to conservation of momentum, things get messed up. And the reason why is because the definition of momentum is not really correct. It needs to be corrected. And I've always envisioned having time to actually go through and discuss where this idea comes from, but I just don't have time. So I do have notes about it, but in reality, I never get to them. And so I'm going to, because of time, just state the results. State the fact that momentum has to be redefined because of relativity. Even Newton's second law has to be rewritten because of relativity. Okay? So I'm going to write the equation for momentum. And this equation then allows conservation of momentum to work in any reference frame based on the Lorentz transformations. Because it's the Lorentz transformations that we should be using now, not the Galilean transformation. Okay, the Galilean transformations are the Lorentz transformation as gamma approaches 1. So we're going to redefine momentum in the following way. That's going to be our new definition of momentum. Defining it this way allows conservation momentum to be valid in all reference frames when you apply the Lorentz transformation. And by the way, Newton's law is going to be written differently too. Newton's second law is going to be written differently. So let me skip a few slides because these describe why we need to change it. Okay. This is the new version of momentum. And I got to say something about gamma because this is not always mentioned. Okay. Gamma here is a little bit different from gamma that we've talked about. Okay. So when we do this, this v is the velocity of the reference frame. That's not the case here. And really what I should have been doing is putting a subscript, gamma sub v, to differentiate, to actually differentiate. I'm going to have to do it now. I'm going to call this gamma sub u because this gamma is associated with the speed of the object. This is the speed of the reference frame. So you need to understand the difference between the two. Sometimes textbooks aren't clear enough in distinguishing those two. Okay. This new way of writing momentum now preserves conservation of momentum in all reference frames, regardless of what the size of the speed is. Because if u is small, what happens to this denominator? It's 1. And we get the classical version. Okay? So in the limit, we get the low speeds, we get what we're used with. But here's the interesting part. What we are replacing here is m with gamma m. That's a mass. But now the mass is velocity dependent. That's a very new thing. Okay? The mass is now velocity dependent in relativity. It's not in classical physics. Okay? Questions on this? Because it's different. Now we can then use this expression.
Professor?
Yes.
I do have a quick question.
Sure.
Equation on the right side where you have delta t prime equals gamma times delta t prime. Are both of those the same, the delta t primes?
This should be erased.
Okay.
Yeah, so I took this delta t, put it here, and wrote gamma. I'm not sure, maybe I'm not understanding your question.
No, yeah, I didn't know that was erased.
Okay, sorry. It didn't erase good, it's too much of a, sometimes I use my hand and it just becomes a smudge. Okay. We can then use this definition of momentum and the work kinetic energy theorem. Remember the work kinetic energy theorem? Work done by the net force equals the change in kinetic energy. Force is dp dt. And we can calculate changes in kinetic energy. Okay. So Einstein did that. and got an interesting expression. This is where you get the famous expression from Einstein. Okay. I have the derivation in your notes. If you are interested, you can look at it. I'm just going to state the results. Again, it's really in the interest of time. I go through it. The notes have all the details because the books sometimes don't. Okay. And you remember classically, kinetic energy, or non-relativistically, I should say, we wrote kinetic energy as 1/2 mv squared. And we will find that's not the case anymore. You can't do that anymore. You can't write kinetic energy 1/2 mv squared in relativity. If you go through and use this definition, the definition of momentum, okay, you can derive an equation for kinetic energy, assuming something starts from rest. Okay, when you do this derivation, you assume the object starts from rest, and you can show that the kinetic energy K is written in a different way: gamma sub u mc squared minus mc squared. This second term is called a rest in energy. This is the energy that the particle has when it's not moving. In classical physics, that doesn't change. So that's why we never see it, because the mass doesn't change. But in relativity, when you do work on an object, it raises the energy of a particle from a rest value to gamma mc squared. What it does is it raises the mass of the object from m to gamma m. The mass changes from m to gamma m. Okay? And this term is called a total energy. So E total you don't see this anywhere here. Actually, I should write this as a U because we've been using U. Okay? So in relativity, kinetic energy is written this way. Not that way. What Einstein showed was that when you do work on an object, you actually are raising the rest mass, which is this term. The mc squared is the rest energy. M is the mass, the rest mass. What he's saying is that mass and energy are placed at equivalent levels. You can get mass, you can convert mass into energy. So you can raise the mass of a particle from m to gamma times m. And the velocity is included in this term. That's the famous E equals mc squared. The whole derivation's there in the slide. And I'm not going to go through it. Just a lot of some calculus and some algebra. So this thing indicates that if energy is added or removed from a system, the mass will change by the energy difference divided by c squared. Energy and mass are related by c squared. Okay. So gamma m is the new mass. Now, for consistency's sake, this equation should approach that one for low velocities. So let's try it. Gamma is one minus u squared over c squared. So let's let this to be true. Now let me write it like this. So you folks learned. I don't want to just set this equal to 0, then I'll get 0 everywhere. Okay, I want to approximate this thing. You've all had Calc 2, and in Calc 2 you've learned how to expand functions. You've learned to approximate functions, and so there's an expansion, a Taylor expansion. There's an equation for this when this term here is less than 1, much less than 1. It looks like this. And maybe you don't remember that, and usually what physicists do, they look it up. Okay, they look up the expansion formulas because we love doing these things. I'm sorry, I missed the question, Matthew. Can you? Oh, you asked about the difference between the U and the V? Well, I'm going to put down the subscript U and V so you can tell the difference. Okay? If it is associated with energy or momentum, then you have to use the speed of the object. And I will write a U subscript. If it's associated with time, then you want V. And again, I would write the subscript V. There are some calculations that involve both of them in the equation. Well, probably not. You'll probably won't see them. Okay. But if it's associated with momentum and energy, it's U. It's the speed of the object. Okay, so you have to make that correlation. If it has to do with time and time dilation and length contraction, that's the velocity of the frame. Does that make sense? Okay. All right, so let's go back to this. This you guys saw this in Calc 2. Okay, and these you look up. Physicists like making hard calculations simple by making these kind of approximations. We call them back of the envelope calculations. Physicists do it all the time. Okay, and so I'm going to rewrite this as approximately equal to mc squared times this term I might have a mistake here. Hold on a second. No, I'm fine. What happens to this term and this term? They cancel. In fact, I'll write it out. So when the speed approaches 0, when u over c is much, much less than 1, then this equation approaches that. So, which is good. This is what we want. Okay? So, the original equation we were using for kinetic energy in Physics 205 was still valid. It's just that this works for low speeds. Now, one of the things you should notice with this term is let's say you want to accelerate an object up to the speed of light. If you do that, how much energy is required? Well, if you get to the speed of light, this is 1. 1 minus 1 is 0. You're taking a number divided by 0. This thing blows up. It tells you it takes an infinite amount of energy to accelerate an object to the speed of light. No, u is the speed of the object in a reference frame. Okay? If you relate u to u prime, then you use Lorentz transformation. If you're using a Lorentz transformation, then gamma has the v in it. We're not doing any transformations here, right? So it's gamma sub u. It's when you do the transformation that you use a gamma sub v. Okay. Now, the conversion of rest energy into kinetic energy with the corresponding rest mass loss, it occurs in decay processes, nuclear fission, nuclear fusion. You see it, the energy being converted, mass being converted into energy, and vice versa, when you look at the structure of a nucleus. I'll give you an example. And we will do that example. We'll actually do the actual calculation because it's really easy. If you take a proton, and you guys know what a proton is, and a neutron, right? These are two subatomic particles. This is a positive charge that has no charge. They each have mass. Now, you can bind them together. You can do an experiment to bind them together into one. And they have approximately the same mass. And I'll show you, I'm going to show you the actual values in a little bit. Okay, they have approximately the same mass. But let's say we bind them together. Okay. This mass is less than the sum of these two masses. Okay? We know that from experiment, that this mass is less than the sum of these two masses. Where did that mass go? The mass goes into binding them together. There's energy stored in the system, and that energy is negative. There's an attractive force. Attractive forces mean you have a negative potential energy. At least when it comes to, let's say, like for example, like the Earth going around the sun, the potential energy between them is negative. Okay, so it goes into binding the system. The fact that you've lost mass here and binding them means that that mass got converted into energy. And it's very easy to calculate the binding energy. It's very easy to calculate how much energy is required to either bring them together or pull them apart. All it is the difference in this mass from the difference in these two masses times c squared. That's all it is. It's really simple. A lot of the problems in the homework, that's all you're doing. You're doing the simple calculation. Okay. Now, in addition to writing the equation this way, you can also write the total energy in the following way. Now, where did that come from? If you take this equation, and we'll just do it, I won't write it as a vector. I'm just going to write it in one dimension. And you solve for that. Okay. So you take this equation, solve for u over c, and then substitute that expression into here. Whatever expression you get for u over c in terms of p, you put it in here, you'll get that expression. Oops. You'll get that expression. Okay, so I have another way for us to write the total energy equation, which is nice. Okay. Let me just say something about this equation. What do you folks know about light? Does light transmit energy? Yeah, light transmits energy. And we describe energy in terms of photons. These photons have no mass. So the energy of a photon is P times C. Just set this equal to 0 and you get the energy of a photon. In chapter 34, they derive an expression for the energy of a photon. It's like this. Okay? The energy of light is just that, P times C, where P is the momentum. P is the momentum of the object. Of course, for a photon, I cannot write P this way because the photon has no mass. There is a different way to write the momentum of a photon, but you're going to have to wait until Physics 215 to learn that. Okay? For us, we can just worry about this relationship here between the energy of a photon and its momentum. But there's another way to write the momentum of the photon. You will have to wait until Physics 215. Okay, I don't want to get to it here. Now, another interesting thing is the quantity E total squared minus P squared C squared is equal to M C squared squared. That's the rest energy. No matter what reference frame you're in, this term is the same. It's invariant. This almost looks like the length of a vector squared. It turns out in relativity, all vectors are written in 4 dimensions. So momentum has 3 components of momentum and another one that involves energy. And when you write the length of that vector, you get this term. Okay. Four-dimensional vectors in relativity are invariant. And a four-dimensional vector, it's the length of it, the distance formula in 4 dimensions. Okay. But you have to write it properly. All right. So, but we don't have time to talk about that here. So I want to do problems. What kind of problems can we do with these ideas? Usually they're collision problems with subatomic particles. Okay? And so I'm going to do a problem. And I also need you to see one of the videos. One of the videos, it is a longer video, I do a collision problem 2 different ways. So I show you 2 different techniques, and those 2 techniques are illustrated in the homework problems that you do in the assignment. I chose 2 problems in the homework, and you're able to do the problems 2 different ways, and it highlights the 2 different ways. Okay, but you watch the video. But anyway, I'm going to do this example. It's a very, very simple example of a collision, and I'm going to do it relativistically. Classically, it's very easy. And actually, relativistically, it's easy too. Suppose we have 2 particles of equal masses moving towards each other. Okay? They collide and stick together. And I'm going to write their speeds u. What do you know from Physics 205 about this collision? They collide and stick together. What's going to happen?
Their final mass is the same, final speed.
Yeah, their final velocities will be the same. What's the final velocity going to be if they have the same mass, same speed, but opposite direction?
Wouldn't it just be 0? 'Cause they cancel
0.
each-
And the reason why, classically, this is what you would say is mu minus mu equals m plus m u final. And since the initial momentum of the system is 0, momentum is conserved, the final momentum of the system has to be 0. Right? And so you get u final 0. You've all done that problem. Your instructor probably did a demo showing this. That when with two cars come together, same mass, same speeds, opposite direction, they collide together, they stick together, and the thing stops. Okay? Now, do you use conservation of energy at all in this problem? Oh, hold on a second. Do you use conservation of kinetic energy in this problem? No. In fact, when you did Physics 205, you don't have to, for the completely inelastic collision, you didn't even consider energy because you only always had one unknown. But what about when you did elastic collisions? When you did elastic collisions, you conserved momentum and kinetic energy, right? When you did elastic collisions in Physics 205, you conserved kinetic energy and momentum. When you did the completely inelastic case, you just worried about conservation of momentum. And if you had something that was in between that was inelastic where the object was still moving afterwards at different speeds, you'd have to know how much energy is lost in order to use conservation of kinetic energy. In relativity is different. We can still use conservation of momentum, but we're not using conservation of kinetic energy anymore. We're using conservation of energy, because whatever energy changes, they result in a change in mass of the system. Okay. Whether the collision's elastic or inelastic, I'm using conservation of momentum and conservation of energy, of total energy. That's the difference between the problems we do here and the problems we do in Physics 205. Okay? That's the only difference, but you know, the ideas are the same in terms of how you approach the problems. Classically, the mass doesn't change. Classically, when these things collide together, the total mass is the sum of these two. Let's do this relativistically. Okay? I'm going to use conservation of energy to figure out the final mass of the system. These things collide and they stick together to form one object. I can write this as the total mass m, or I can write it as 2 times these individual masses. Okay, so and granted, I stole this problem out of a book. The book wrote it as 2 individual masses stuck together. Okay, so I'm gonna stick with that. So, if I use conservation of momentum, I would do this. Okay, but this does not allow me to figure out what the new mass of the system is. I actually have to use conservation energy to find the new mass of the system. So, here's the equation for total energy. This particle is going to the right with speed u. So first particle has total energy. Has total energy gamma sub u mc squared. Second particle has total energy gamma sub u mc squared. The total is 2 gamma u mc squared. That's what I started with. Okay, so total initial energy equals total final energy. So I get 2 gamma sub u mc squared. Now what's my final energy going to be? What's the final speed of the 2 objects after they collide? We know that. It's 0. So what's gamma going to be? It's going to be 1. Gamma is 1 after the collision. Gamma sub u equals 1 after the collision. because U final equals 0. So M final is equal to 2 gamma U M. And U is the initial velocity. Oops. So, since this term is bigger than 1, then my final mass is greater than my initial mass. The final mass is greater than the initial mass because the kinetic energy of the particles is turned into heat. Right? That's what happens when objects collide. That's it. That's how you do a conservation of energy momentum problem. I'm going to stick through this problem, and then so that you guys can do the homework. I'm going to do this in 2 reference frames. If you need to leave. That's fine. Okay, but I'm going to finish this problem so that you have enough information to do most of the homework problems. Okay, and I do need to talk about a couple more things on Monday. So I thought you can do all the homework problems, but maybe not. I needed to talk about one more thing. But if you need to leave, that's fine. I'm going to keep videotaping this problem. Okay. Now, this is the new mass. So I want to show you something very interesting. Okay. Let's go back to the classic problem. Okay. Classically, or basic physics 205, the total initial energy of the first particle is what? It's going to be 1/2 mu squared. The total initial energy of the second particle is 1/2 mu squared. So each particle has this much kinetic energy. The total is mu squared. So from physics 205, if we looked at the total energy of the system, kinetic energy of the system, it's just mu squared. They collide and stick together. What happened to the kinetic energy? When you did this in 205, what happens to the kinetic energy? Goes to 0 because U final 0. So you've lost all the kinetic energy, and it's converted into thermal energy, and probably sound energy too. Well, let's calculate the difference in rest energy of the particles. I want to calculate the difference in rest energy of the particles. So before, the rest energy, each particle had mass m. So the rest energy was mc squared. Afterwards, I have m final c squared plus m final c squared, which is 2 m final c squared. But m final is gamma u m c squared. So let's calculate 2 gamma u mc squared minus 2 mc squared. So what do I get? I get 2 times mc squared times 1 minus u squared over c squared to the minus 1/2 minus mc squared. Okay. Let's let this, so that to make the example more clear to us, let's let u be small. Then I'm going to go back and use my approximation. And so the change in energy is really the change in kinetic energy of the system. The change in the mass is reflective of the change in kinetic energy of the system classically. This shows you that the energy loss, the increase in mass, is due to the fact that you've lost all the kinetic energy. Okay? Oops. I want to do it from one more viewpoint. Same problem, one more viewpoint, because it allows us to work with the velocity transformations. And I'm not going to go through all the algebra. I'm just going to set it up, tell you to do the algebra, and then that's it. Okay? And then I'll be done for the day. And again, thank you if you're staying with me. I'm going to do the same problem, but from the reference frame of one of the objects. Okay, I'm going to do it from the frame of one of the particles moving to the particle moving to the right. So pretend you're sitting on this particle. Okay, and you're going to slam into this other guy, this other particle going that way. So according to you, you're the unprimed frame. I got to fix that figure. You want to find the speed of this object relative to you. According to you, if you're moving to the right, all objects on the earth are moving to the left. Okay, so the earth is moving to the left. And this object is launched from a vehicle that's moving to the left. And so u, if you use the equation u equals ux prime minus v, that's a plus, sorry. Here, u sub x prime is minus u, and v is minus u. Then I get the following. the u sub x is minus 2u over 1 plus u squared over c squared. So we see this object coming towards us at the speed notice I said speed. Okay, I didn't put the minus sign there. And we're stationary because I'm sitting on the object, so I'm moving with the object. The object is stationary relative to me. The Earth is moving to the left. This object is coming towards me at that speed. I want to use energy conservation to solve this problem. Again, total initial energy equals total final energy. So if this guy is not moving, the only kind of energy I have is a case where gamma is 1, because the momentum initially of my particle is 0. So the total energy I have is just mc squared. This particle is coming towards me. At that speed. And so its total energy is given by that. And it's a very complicated thing. I'm going to have to write that all out. And afterwards, these objects stick together and they move with the Earth at the speed u. Okay? They stick together and they move with the Earth. That's the same thing as saying in our frame it's not moving. So what's gamma sub u? So this one's going to be messy. Because u is this monster. Now, if you go through and solve this problem, you should, and I completely solved it in your notes, okay? You will find that you will get the same answer. I shouldn't write u, I should write gamma of this thing. I don't want to write that whole thing out. Okay? And it's a good exercise for you to go through and solve this for M final. And no matter what reference frame you get the same final mass. That has to be true. The mass has got to be the same in all reference frames. Okay? Even though it's changed, every reference frame is going to give you the same mass. I can also do the problem from conservation of momentum. Okay? I can also do this using conservation of momentum. And I can get the same result. What does conservation of momentum give me here? Well, if I'm sitting on the particle, then this object doesn't have momentum. If I'm sitting on the particle, all the momentum is from this object. And so my total initial momentum is going to be gamma mu. But u is, hold on. U initial, I write it that way. But U initial is this thing. And then gamma is a complicated equation. Hold on a second. So gamma is a complicated equation. I know the algebra looks nasty, but it's not that bad. And then the final is going to be the two masses, the two final masses. And since it's moving the Earth's frame with speed u, to the left, the minus signs I cancel them because everything's moving to the left. Oops. And if you solve for m final, you get m final is gamma m. You still get the same result. No matter how you do it, you get the same result. Okay, now I did skip the algebra. The algebra is a little bit messy on here. Okay. So I wanted to go through this example so you have some examples of using conservation of energy momentum. There is one in the modules, the last one. It's a longer example, and I do it two different ways. Same reference frame, though. So I do the problem in the video in the same reference frames, but I do it two different ways. In one method, I actually focus on using this equation, and in the other method, I focus on using this equation. I'm trying to give you as many ways to attack the problem as you can because one method sometimes will be easier than the other. And they are highlighted in the homework. So really the only thing I got to do is the problems involving mass changes in terms of forming in terms of like fusion reactions, etc. And those problems are easy. We're going to do those on Monday. So if you stayed with me, thank you. All right, so we'll see you. Oh, actually, we'll see you on Friday.